Afternoon Year 12. Now I'm not there to teach you guys, so I've made this video so you can still carry on with the content. In our chapter Geometrical Applications of Calculus, we're actually up to this part of looking at different types of stationary points. Now there are three types of stationary points, and I just need to go over them and explain them, and also think about the nature of the stationary point, which is very, very important. So one of them is called a local minimum. The reason why we call it local will become a little bit more apparent later on, but let's just say we have our class right now. Who's the tallest student? Ewan, maybe? He's probably the tallest student, but he is the local, more relative tallest student compared to the rest of the students in the school. So he might be tall in our class, but he's not as tall as some other kids amongst the school. So he's the local tallest kid, or relatively tall compared to everyone else in the classroom, but compared to the school, he might be a little bit shorter. And that's why we get our local minimum. So later on, we will look at that these locals only apply to this specific area, okay, or this specific box. So with this, our local minimum, we've got this line, this parabola that comes down, okay? Its gradient is is in negative, and then it hits some point where its gradient is going to be 0. That is going to be our stationary point, that the gradient doesn't change. That's why it's called stationary, okay? 0. And then from there on, our gradient will be positive and keep going up. And so the textbook has this little table, which I think is kind of useful. If we have our x, our left-hand side, our minimum, and our right-hand side, in case you don't know what those RHS and left HS stands for, if we were to take any function and we differentiate it, we can check that if it's a minimum, it should meet these standards. That at fx, or y dash, on the left-hand side, it should be less than 0. That is, it should be negative. At our minimum point, it should equal 0. And on our right-hand side, it should be less than 0. That is going up. Okay? Or we should put y dash in there, just to make it a little bit easier to understand. Okay? And I've also put these green lines in, basically negative, horizontal, going up. Our local maximum is the maximum point in which this parabola gets to. Okay, it peaks out. The max, or having like a max volume on your phone, is the maximum in which it can go. This is the maximum in which a parabola can go at this local area, this local point. So our gradient is always positive, hits a 0 gradient at some x and y value here, and then keeps going down negative in a negative gradient. Okay, so at our x, if we differentiate it, any function, y dash will be greater than 0, that is positive, going up. Our maximum will equal 0. And our right-hand side, our y dash, will be less than 0, that is going down. Okay, sometimes it can get a little bit confusing trying to think in terms of this. I know I get trip up sometimes, because you're going from two different, in some ways, dimensions between each other. You are very used to the x and y kind of stuff and looking at functions and curves and sketching them. But when you're thinking about derivatives and thinking about the curves and the nature of those numbers, you've got to be thinking on a different dimension is probably the best word I can think of right now, but it's a different how you evaluate it. Okay? Sorry, our third point is our point of horizontal inflection. And this is where it's monotonic, where our function will keep being positive and then reach some stationary point and then continue to be positive. It doesn't actually curve back around. This one, it goes negative, hits a stationary point, and then goes negative again. And therefore, if we take any function and we can meet these criteria, it should be a horizontal point of inflection, either positive or negatively. If we differentiate it and our left-hand side is less than 0, that is positive number, then goes 0, and then goes positive again, it's going to be a point of inflection along as a positive kind of cubic, I guess you could say. And then our alternative of that would be a negative, where y dash is going to be less than 0, y dash can equal 0 at our inflection, and then y dash is going to be less than 0. And I've drawn this little picture just to help you guys understand, looking at local minimums and maximums and why we call them locals. If we have some kind of function, I guess, like going like this, it's curving up, hits a point, curves back down, hits another point, and it goes back up, like pinball. Just within here, we can say that this is, just here, a maximum. It peaks off here. If we were looking at this, just that part, that would be our local maximum. But the thing is, as the function continues, it actually keeps going up, and that this is actually relatively small compared to the other values that it can be. So, all these points. So this is only a maximum within its set box, within the area that we're looking in, within the confines. Similar to the example of the classroom, who's the tallest kid in the classroom compared to who's the tallest kid within the school. And this, even though yes, this is a local minimum, there are x and y values that continue further down. So this is only a local minimum within its set box that we're looking at. Okay? That's kind of the reason why we say locals, maximums, and minimums, because these functions can continue and go on to infinity and change in nature. But let's do a question. Let's try and deepen your knowledge so you understand. So this is question 1 in our textbook. Find the stationary point on the curve y equals x squared and show that it is a minimum point by checking its derivative on both sides. Okay, there's a few different steps and I'll write them out for you guys because I know some of you like steps. The first thing we want to do is differentiate this. Then, I'll write that down. If I can find differentiate, if I spell it wrong, deal with it. 2, I want to find my x, find x value for the stationary point. You might want to copy this down, guys. And remember, that is going to be y dash equals 0. 3, I'm going to have got my x value. I want to sub that back into sub x value of stationary point. Back into original function. To find y value of stationary point. Okay. Then lastly, we're going to check the nature of the function. Yeah, that's all right. We'll call it that. The nature of the function either side of the stationary point. I apologize for my writing, and I apologize it's in red. I should have written in black. Okay, let's go through this. Let's go through step 1, okay, where we're differentiating. So here we have y equals x squared minus 1. Let's differentiate. Y dash is going to be 2x. Okay, now that's our differentiation. We want to go on to step 2. That was really easy. Step 2 will be find the x values for the stationary point where y dash equals 0. Okay, so step 2. Y dash, and I really just want to put this out there firstly. Y dash equals 0. Now, I know a lot of you will get sick of writing this, and you'll say, why we keep writing it, sir? It's just good habits, okay? I don't want you guys to pick up bad habits and do sloppy maths. Just state that y dash equals 0. So your marker and whoever's reading this mathematics, and you know that what you're doing, okay? Have that clarity of thought in your writing. Also write neatly. so you know exactly what you're doing. Okay, so y dash equals 0. So what we can say then is 0 equals to x, just taken from here. Okay, if y dash equals 0, it's going to equal 2x. 0 equals 2x. We can divide both sides by 2, and 0 will equal x. Therefore, x equals 0. Okay, so that is the x value for our stationary point, just here. So what we can do with this now is sub the x value of the stationary point back into the original function to find the y value of the stationary point. That is only our x value. We want to find our y value. So let's do step 3. So, where's our original function? Here it is. Y equals x squared minus 1. Sub in x equals 0. We have y equals 0 squared minus 1. And that is going to be minus 1. Okay, so we can say, therefore, our stationary point is going to be 0, negative 1. If we were to draw that, we would say, okay, 0, negative 1, here's 0, 0, negative 1, just here. So our stationary point is 0, negative 1. It is just at that point. Now we've got to prove that's a minimum. We're going to prove it's going to be curving down like that. Okay? The way we prove it is we're going to use our differentiation just here, our y equals 2x. And we're going to sub in different values of x either side of here. We're going to probably just go one to the left and one to the right. So 1 to the left would be, the x value would be negative 1. And 1 to the right, our x value will be 1. And we're going to take those two different values, plug them into our differentiation, and that will tell us the nature of them. They should be either less than 0 or more than 0. And based on that, that will tell us, based off the rules we looked at before, whether it will be a minimum. Okay? So if that were true, let me grab the right sheet. Our left-hand side, our y dash should be less than 0. And our right-hand side, our y dash should be greater than 0. Okay? So we're getting a negative number and a positive number. So don't be defunct here. I'm just going to move our sheet up a little bit. And I'm just going to cut down to this side. Sorry, it's a little bit messy, guys. So 4. Check the nature of the function either side of the stationary point. That's what we're doing. Okay, so we're going to test. Let's test this. Test. We're going to do left-hand side first. Just good to go from left to right. That's the way we read. Left-hand side, and we are going to test with x equals negative 1. Okay, let's put that in our differentiation. Y dash will equal 2 times negative 1. Okay, remember we're taking from our differentiation just here. Okay, so we're taking that and putting it into here. And that would be minus 2. Okay, well, that is y dash equals negative 2, excuse me, is less than 0. Minus 2 is less than 0. So everything's looking good. It's already curving down. So we can add just to here. Okay, things are curving down just here. I'm making a bit of an assumption. I know it's just negative 1 I've used, but I have proven that it is negative just here. Now, if we're looking at our right-hand side, so this side of it, let's test right-hand side. Let's go x equals 1. Let's go just where here, 1. So y dash, we're going to substitute in our differentiation, 2 times 1, which is 2. And because 2 is greater than 0, just as in here, we're going to have a positive side, positive gradient. Okay, because y dash tells us the nature of the line. Okay, thinking in 2 different dimensions here. It's hard to flick between them. Trust me, you'll get better at it. It's muscle memory. So it's going to be curving up. So that's going to be positive. Okay, so we have proven it. Just to make sure that we do it properly, the textbook answers like this. It says the stationary point is 0 minus 1, which we proved. And then they say left-hand side, y dash, why did I write a capital? Sorry, let me start again. Sorry, it's late, guys. Left-hand side, y dash is less than 0. And then right-hand side, y dash is greater than 0. Okay, and that's how they put it. I like to just draw the picture for you guys so you understand, but it's this negative value and this positive value. Remember, thinking about this last step is probably the hardest. Okay, can you guys please copy these rules down? Okay, you can just pause the video and copy them down. Sorry they're in red, I probably should have written in black, but I hope that sets out exactly what you're meant to be doing.